Here's our goal. We're going to walk through briefly the class opener together because we spent some time on that FRQ. Here's our goal. We are going to use integrals to find an area between two curves. Big vocab here, guys, that you're going to see is the word bounded. We're going to find bounded areas. Bounded means that it's contained. It's got something that keeps it from being infinite. We're going to find bounded areas today. As a quick review, take a look at example 1. They're giving you a graph of a parabola moved up 1. They're asking you to find the area under the curve from x equals 1 to x equals 2. I'm not going to go through all of the calculations of this, but will you please write down an integral that represents that area, and then I'll come check. You should have had this integral, -1 to 2, x squared plus 1 dx. You get that? Okay. Anybody have a value for that? Anybody go so far as to evaluate it? 6. Lots of people got 6. We're good with that? Okay. Second one now. We're going to move from net area to total area. So example 2 is asking for this plus this. This calculator scale isn't very good. That intercept is x equals 1. That intercept is x equals 2. And if you graphed it on your own calculator, hopefully you came to that conclusion. Okay? How do I find that area? Can I do it with one integral? Or do I need 2 integrals? Kind of depends if you get your calculator or not. Okay. If you have your calculator, you can do this. The absolute value on the function takes everything that's below and just reflects it above the axis. If you have your graphing calculator, you can do that. I think on a problem like this, more often than not, you're not going to be allowed a graphing calculator. How do I do it if I don't have a graphing calculator? What do I need to do? Can I do it in one integral if I don't have a graphing calculator? Where do I have to break it up? Great. I have to break it up where the curve first goes negative, and I'm telling you that that's x equals 1, even though it doesn't look like it on the scale. You're going to integrate that function, 3x squared minus x plus 3 dx. And then you can do this notation a couple of different ways. I'm going to subtract the integral from 1 to 2 of that exact same function. Which one? Right here? That's supposed to be a 3. That better? Okay. If you were doing it by hand, you would need 2 integrals. If you're doing it with a calculator, you could do it in 1. Okay? Question. Questions, why did I subtract them? This one is above the axis, so it's going to count as positive area. This one is below the axis, so it's going to count as negative area. And since I want it says, I should have put the word total in here. Find the total area of the region bounded. I want this area to count as positive. Since the value of the value of the definite integral is negative, if I subtract it, I'm going to end up adding it. Okay? Good so far? All right. Let's dig in. Let's answer that question that we had up at the beginning. I was going to do a GeoGebra demonstration here, but it didn't go well, so I'm going to skip it. All right. First one we have 2 weird curves. The functions aren't given. I want to show you what I mean by bounded area. Okay? On that picture, there's a parabola and there's some sort of a trig function. Which area is bounded is answered by this. This area is bounded. Okay? Everything outside of that is unbounded. So we're going to have functions that give us a region that has boundaries. That's what it means by bounded. Okay? There is area over here between the curves, but I'm not going to shade it because it's not bounded. There's an infinite amount of area up there. And we can't find infinite areas at this point. Or ever. Depending on how far mathematical science advances over the next 1,000 years. But we won't be around for that. All right, so this is the area that we have bounded. Now, based on what we already know, I'm going to do some shading, and you tell me if it makes sense. Okay. I want the area that's shaded in blue, but the tools we have at this point allow us to find regions that are underneath a curve and above the x-axis. That's the way we created Riemann sums, right? Okay. So if I were to draw here and here, and I'm using these on purpose, there's intersections here. Those are the x values. x1, x2 actually we'll be consistent here. How about we use a and b? We're going to integrate from a to b. Okay. If I integrated under this trig function from a to b, I would have that region shaded. You with me? Okay. How is what I just shaded with red pen related to what I want? It's a little bit too big, right? How much too big? What I shaded with red is this. Let's call the trig one f of x. Let's call the parabola g of x. Okay? What I just did was the integral from a to b of f of x dx, right? Okay? I'm going to shade a couple of slivers here. I'm going to shade this sliver and this sliver. And those two slivers I just shaded represent what? Okay, that is the area under g of x, right? What do I have to do to those two to get what I want? Subtract. Is there a property of integrals that allows us to make that expression simpler? A couple of nods. Property of integrals that allows us to make that expression simpler. What is it? What can I do? Put them together as one integral. Why can I do this with this case? They're both from a to b. If your boundaries are the same and you're subtracting integrals, I can write this as one single integral. Actually, I need to lop off one of those dx's, and I should probably write it this way. Okay? That, friends, is a formula for area between curves. Okay? Now, to make this a little bit more universal, I'm going to add a couple of words underneath here. F of x, this formula will work if f of x is your upper function and g of x is your lower function. If f is above g, this works. If g is above f, what's true? If g is on top and you did f minus g, what would you get? Same number, opposite value. Okay? So if you did upper minus lower, or if you did lower minus upper, you'd get the same absolute value, but it would be a negative. Okay? That's what we're doing today. And I want to apply it to the next example, and I want to have you dig in a little bit. Okay? Because this one looks a little bit different than the one we just did. The first example is always the easiest, right? Why is that one easy? Because we got a red area above, a green area above, and we got a blue area, and we're all happy because it's all above the axis. What happens when it's below? Do we need to worry about it? That's what I want to go to next. So, find the area of the region bounded by a line and a parabola. I've given them to you already. Okay. And if we were doing this problem whole from start to finish, a lot of times you would be asked to find, or you'd be required to find those two. Why? Because that's A and that's B, and those are the intersections. Is there an easy algebraic way to find intersections if I've got two functions of x in terms of y? Set them equal. So the first thing I'm going to do is find the intersection by going x plus 4 equals x squared minus 2. This is our old friend quadratic. You can use quadratic's formula if you'd like. But more often than not, if they give you something like this and the functions are nice, you're going to be able to use factoring, and it's just going to be a lot easier and faster than using your calculator. So if we rewrite this in general form, yay. I put that on the same side. Factor. If you're not fluent at factoring yet, you want to keep working on that. Minus 3 and plus 2 works, doesn't it? So my two intersections are at x equals 3 and x equals negative 2. I'll go ahead and label those on my graph instead of A and B. This is negative 2, and this is 3. Okay? Good so far? Based on what we just talked about, here's the question I want to ask. Question is that the appropriate expression to use for this integral? I want you to take a minute and talk to somebody near you about areas. If I shade some areas here, the first, you know what I'm going to do? I'm going to put another integral on this just so we can talk about the areas separately, but we're okay that those could be one area, right? Okay. So let's talk about blue first. Okay? This first blue integral represents what shape? A trapezoid. It's this thing, right? That's that trapezoid. Okay? It's not exactly what we want, but it's in the ballpark, right? Okay? What now needs to change to get us to the final bounded region? What do I need to take away? I need to take away this sliver, right? And I need to take away this wedge. Bonus points if you can distinguish between a sliver and a wedge. Okay? I need those two to go away. You with me on this? What else needs to change? I need to add the bottom part. I need to add that portion. Okay? Now, I think what you're going for at this point is you need to make this second portion 3 separate integrals. Are you with me on this? Okay, in theory, you're correct. If I take that red integral, I don't know what these are exactly, so let's call this one A and this one B, just for sake of naming them. Okay? Would you feel better if I wrote this red portion as the integral from negative 2 to A of x squared minus 2, and I would subtract that part, right? Right? And then my next integral is going to be from A to B of x squared minus 2. And my last integral is going to go from B to 3 of x squared minus 2. I got an extra x on this one, guys. Sorry. Those are the 3 portions that would make up the red area, right? Good so far? Okay. We all agree that the last one and the first one should be subtracted, yay? The one that gets in the way in the middle is the one in the middle. What is the value of that integral? What do I want it to be? How can I take a negative area and add it? I could do an absolute value. I could switch the B and the A. Will you entertain this thought for a moment? What if I put a negative in front of it? Would it work out okay? Because if I subtract a negative number, what am I really doing? I'm adding it. I'm trying to make a case for saving you work. Doing all this would be okay as long as you're careful. But I want you to know that if I take a look at this equation that I wrote right here, I'm taking the blue part, which is the area under the upper, and I'm going to subtract the area under the lower. And by default, because there's a minus in front of this whole silly thing, there's a minus in front of it, it's going to subtract this red, which you wanted it to subtract. It's going to subtract this red, which you wanted it to subtract, right? And it's going to subtract this negative. And when I subtract the negative, what's it really doing? It's adding it. Isn't that cool? That's a long way of saying this formula works. This is what you want to do. The bounded area is always going to be the integral from a to b of the upper function minus the lower function. I've got another picture that's going to help you in just a moment. The beauty of that formula is it works even if all of your function is below the x-axis. You just have to identify which function is upper and which function is lower. Okay? Here's the picture I want to show you. Okay? I want to relate it back to Riemann sums. I'm almost done today, too, guys. I want to relate it back to Riemann sums. Okay? I've got an upper function, call it f of x. I've got a lower function, call it g of x. Okay? If I think of area as the sum of an infinite number of rectangles, I now need to find out what is the height of that rectangle? What is the height of that rectangle? What is the height of that rectangle? And so on, right? It's easy if all of the functions are above the axis. I've got a function value, f of x1, minus a function value, g of x1, right? That pretty clearly gives us the vertical height we want. Upper function minus lower function. With me? Okay? But the weird thing that we just encountered is something like this. This height right here is f of, it uses x sub I. That's f of x sub I. That's a general rectangle. Okay? What's this value down here? That value down there is g of x sub I. A positive value minus this negative value will give you that entire height of a rectangle. Does that make sense? Hopefully. It just adds to the fact that we can just do upper minus lower and we can do it in one integral. Long way of getting to a simple formula, I think. Okay? Other type of problem, then I'm going to help you set up a couple of your homework problems. This is the last example in your notes, and then we're going to move to homework for one or two of these. Okay? And I guess if I were to put a phrase on this, I might say that the upper function changes. And these can get very complicated, but if the upper function changes, you need a new integral. Okay? And I think visually this is easy to see. If I break it up at that intersection, this is an area under a square root curve, and this is an area under a linear function. Visually, does that make sense? This isn't area between curves. It's just two different Riemann sums that's going to get you to a final answer. Okay? So, what do we need? We need to find out where that dot is. Want to do it algebraically? Or do you think you can just do it? Should we shortcut it a little bit? The points are on the square root of x. 0, 0, 1, 1, 4, 2. Is 4, 2 also on that other function? Is 4, 2 also on that other function? Yeah. So you can kind of reason your way through it without actually doing all the algebra. Is that okay? Here's my two integrals. Integrate 0 to 4 square root of x dx plus integral 4 to something negative x plus 6 dx. What's the upper bound of the red integral? Linear function starts at 6, slope is negative 1. Where's it going to cross the axis? Six, right? There's your two integrals. I'm not going to go through the evaluation of them at this point. I want to set you up on a couple of your homework problems. Okay? Okay? I want you to start by, and I'm going to check with you in a little bit. I want you to try to do as much as you can without a calculator on this. I want you to set up an integral for 5. Now you're going to determine the area on your own later on. I want to see your setup of the integral for problem 5 and problem 7 before you take off today. Problem 7, you're probably going to want to try to use a calculator. Try to resist the urge. Okay, you do need a calculator to actually do the evaluating, but try to do the setup without a calculator.